Hey guys, you're watching Python tutorial videos on my YouTube channel, Python for Microscopists. In this tutorial, I'm going to talk about deep learning. Basically, why is it called deep? Why is it deep learning? And what do we mean by neural networks? Okay, and along the way, I'm also going to provide explanation to certain terminology and hopefully by providing this explanation it makes it a bit more clear why and how the implementation is done in Python. So before jumping into or before taking a deep dive into this deep learning, let's have a quick look at what the traditional machine learning looks like. So for that, let me open the code that we have written in the previous tutorial where we went through feature engineering and then using random forest for image segmentation. So let me go ahead and open the Spider interface, and this is the code that we have written in the previous 3-4 tutorials. So here we imported an image that we would like to use for training and converted that to a gray level image and created a data frame because we wanted to store all the features, or feature vectors in our data frame. So we started by adding our pixel value itself from our original image as one of the features. We reshaped it into a single a vector, into a single column. We added that to the data frame. And then we actually generated a whole bunch of Gabor responses from our image. And again, Gabor is a convolutional. It's a kernel when it's applied to our image. When you convolve that kernel to the image, it provides certain response. And then we generated about, I believe, 32 different Gabor responses by iterating through or by changing it, changing the theta value, sigma, lambda, and gamma. So that's all these got added to the data frame individually. And then we also added a few additional features such as canny edge, Robert, Sobel, Shor, and Pruitt, Gaussian with a sigma of 3, Gaussian with a sigma of 7, and median. And finally, we also added another column to our data frame where, basically it labels the image, right? So this is our training data. So we added the labels for each data entry. And now we took all of this data, okay, and then defined our x and y, x being our independent variables and y being the dependent variable that we're trying to predict. And then we further split the data into training sets and testing data sets, and basically fed the random forest classifier. I mean, defined a model for random forest classifier and fitted that model using the data from the training data sets for X and Y. That's pretty much it. And then we predicted that on the testing data set and we reported the accuracy. This is the These are the steps that you follow for any machine learning, right? You create a model. First of all, you get your data in order, okay? And then you create a model and you fit the model and basically verify the accuracy of your result. And if you like the accuracy, go ahead and save that model. So in this example, we've used Pickle to save the model, so we can predict future images using this specific model. Okay, so this is a quick repetition of what we have done in traditional machine learning, and believe me, this is very important to understand the next few steps. Okay. And now let me jump back to my presentation. I usually hate presentations or PowerPoint slides, but I thought this is the best way to summarize what I would like to say rather than draw it using my digital pen. So a quick summary of whatever I mentioned in the last 3 minutes. Okay, this is a quick summary of our traditional machine learning using a data set, in this case, a malarial infected versus healthy cell example. Okay, so this is, let's say, a malarial infected image. And from this image, we generated a whole bunch of features. The feature number one can be the pixel value itself. Feature number two is Gabor 1, Gabor 2, Gabor 3, and so on. And then we had Sobel, Pruitt, Gaussian with sigma 3, Gaussian with sigma 7, and so on. So all of these, each of this frame represents a feature that we generated. Yeah, and at a pixel, when you look through these images, that is a feature vector. Okay. So we took this and used random forest to basically train it, and then we can use that to predict whether it is infected, or healthy, right? And a good thing about random forest, again, I should have shown this in the code, is it actually predicts, actually, it's worth repeating, it's worth going up there. Well, I guess we are not printing the feature importances, but we are not printing it here. But the good thing about random forest is it actually gives us the feature importances. In other words, uh, for each feature, it actually assigns a weight. Okay, it's saying that okay, for feature number one, it contributed by, I don't know, 0. Let's say 3, and the next one is not that important. Its contribution towards the final result is 0.003. So and so on. So we get some weights, and those weights are actually assigned during the training process. Okay, so this is traditional machine learning. So what is deep learning now? So deep learning, as you can imagine, is going through not just one type of learning, but then it's actually going to different depths in terms of learning. So here is a graphic to summarize deep learning using the same example. Previously, we had only this first layer, right? Let me go back, only the features layer. Now I'm going to rename the features layer as the convolutional layer. If you think about it, this is nothing but the convolutional layer, right? I mean, we are actually generating a kernel, whether it is using Gabor or whether it is using, Sobel or one of the other kernels. We are convoluting this image with that specific kernel. So think of this as your convolutional layer. And next comes a pooling layer as part of your deep learning, okay? And I'm going to explain what that is in a minute, okay? So you have layer number one, you have layer number two, and then you have a dense layers. Okay, so the output from here is going into this dense layers, and then finally it's going to spit out the outputs. In this example, it can be either infected or uninfected, or not infected or healthy. Okay, now it is called deep learning because it's not just one single layer. In fact, you can actually put multiple convolutional and pooling layers. Okay, so the original image, instead of going through only the convolutional and pooling, you can actually say, okay, I want to do convolution first, pooling followed by pooling, another convolution followed by pooling, another convolution followed by pooling. And why do you want to do that? Well, apparently that really helps improving your accuracy. Again, all of that only valid when you have hundreds or thousands of these training images. Okay, if you don't have thousands of these training images, then the random forest that we worked with is probably a better bet for segmentation type of purposes. And eventually, the output of the pooling layer 2 is going to go into the dense layers after we flatten the images. Okay, and let me now explain a little bit about the terminology. Okay, now again, don't get intimidated by this code that you see on the left hand side. Literally, this is how we are going to define these layers. Okay, convolutional layer 1, pooling 1, 2, pooling 2. So that's exactly what I'm doing here, saying convolution 1, pooling 1, and then I'm doing something called normalization in between, and then dropout, and then going to convolution 2, pooling 2, normalization, drop. Okay, and then I'm flattening the data and going into these what we call hidden layers or dense layers, and same process. So it's literally one single line to define each of these steps in Keras. Keras makes it easy. And again, I'll explain that. So a few keywords to understand before we jump into any coding. Okay, as you can see, some of the keywords I took out of here. TensorFlow is one because that's the library that we will be using. Keras, you see, I typed Keras here, so you should understand what that is. Convolutional 2D, the stuff that I typed up here. Let's understand what max pooling is, what is batch normalization, what is dropout, what is flatten. I just want to quickly, at a high level, explain this. Okay, I'm not going to go into any detail. Each of this topic is a research topic by itself, so there is no way I have all the information to provide you the relevant information. If you really want to take a deep dive, you can go ahead and Google search any of these topics. Okay, but I'm going to provide the summary at a high level so you're dangerous enough to go and explore it further. Okay. So let's start by understanding what TensorFlow and Keras basically are. Now, TensorFlow is again, I put some text here, so in case you want to pause and read out, that's fine. But TensorFlow is the most famous library used in the production for deep learning models. Okay, so you can actually not use Keras, just use TensorFlow for your machine learning purposes, but TensorFlow is not that easy to use. Yeah. Keras is a high-level API built on TensorFlow. If you don't understand what that sentence means, Keras actually uses TensorFlow functionality, but makes it easy and more user-friendly than TensorFlow for us to quickly build and test these networks. Okay, so that's the what TensorFlow is. So TensorFlow will be there when you use Keras. Okay, and Keras makes it easy for us to code these complicated machine learning algorithms. Okay, so now let's understand what convolution and max pooling are. Okay, because these are the first things that we are going to do or define as part of our network. So the convolution layer itself, okay, as I mentioned before, this is a convolution. Let me explain this. Again, I copied this graphic from the following link, so go ahead and go to this link if you want to learn more about it. But convolution is nothing but, let's say this is our original image. Okay, in this example, the values are just 0, 1, 2, but if it's an actual image, you have values from 0 to 255. It's a 8-bit image, right? So a convolution is nothing but you have a kernel in this example, or you can call it a filter. In this example, the kernel is -1, 0, 1, 0, 0, 1, and 1, -1, 1, right? So you have this filter, and you apply this filter onto your original image and do a convolution, okay, type of multiplication. So when you do that, you end up with a number right there, okay? And then you move the filter. In this case, looks like the stride is 2, which means I'm applying it here and then moving it 2 columns to the right. Okay, you see that? 2 columns to the right, 2 to the right, and then come back, 2 to the right, 2 to the right. So each time you do that, you actually end up with a specific number from this matrix multiplication that's going on within, or from the convolution that's going on from within this kernel. Okay, so a 3 by 3 kernel on this image, 7 by 7 image, with a stride of 2 is going to give us a 3 by 3 output. Okay, again, I hope you understand this. If not, you can still go ahead and create your networks, use it and everything, but it really helps if you understand how you're designing, why you're designing something, when you're designing a network. So this is the convolution. So once you do the convolution, what are you going to end up with? Okay, some response, right? Max pooling is literally, it's a very fancy name of actually picking the maximum number. So if this is what you end up with, okay, if this is the matrix you end up with, then with a 2 by 2 filter, let's say, okay, right there, 2 by 2, 2 by 2, 2 by 2, and 2 by 2, you're just picking what the maximum value is. So within these 4 blocks, the maximum value is 6. So that's what you're picking. Here 8, here 4, and there it is 7, right? So after max pooling operation, you're actually getting the maximum pixel value within whatever the filter size that you're actually selecting. Okay, this is what max pooling means. Okay, I hope this makes sense. And there is also other types of pooling called average pooling or mean pooling. I don't know what the official term is. I think it's average pooling, where you average all the values and then put that value up here. But max pooling is the one that gets most commonly used in convolutional neural networks. Okay. Now, before moving on to the next set of convolution and pooling, yeah, if you remember again, what we did here is convolution layer 1, pooling layer 1, convolution 2, pooling layer 2. It helps if we do something in between these steps to enhance the results. Let's say, so one of the things that we typically do is called batch normalization. It's like I said here, it's important to keep the values in the input and also in the hidden layers, right? Within certain range. And why is it important? Because normalization makes sure that there is no activation that's gone really high or really low. Okay, by normalizing, you're actually bringing all the values within a certain range. And typically it improves the training speed, almost like on the order of a magnitude. And again, another side effect or another reason why normalization can be very useful is it allows each layer, that we are defining in a network to learn by itself and a little bit more independently compared to the other layers. Okay, so each layer is almost like an independent layer once you do this normalization. Again, like I said, this topic again can by itself be a PhD topic. So if you want to dive into it, you can go ahead and dive in. My knowledge when it comes to these batch normalizations and everything is I know what the effect is, and I change these things to see how the result gets affected. But obviously, once you dig into this, I don't even pretend that I understand, the research that went behind, these normalization and other topics. So after normalization, you can actually include a dropout step. And the dropout refers to dropping out of neurons at random in a neural network. For example, if this is the neural network, okay, that you have where it's going from one neuron to the other. Again, I'm going to get into this neuron topic in a second. Then instead of connecting every neuron to every other neuron, we are actually randomly dropping out a few of these and only connect the ones that are active. When I say dropping out, I think it changes the weight to 0 or the activation function to 0. But either way, this neuron is dead. We are only using the live ones. That's what dropout basically means. Okay, and why do we do that? The reason is it's needed to prevent overfitting. So it's almost like a regularization method for convolutional neural networks where dropout helps minimize this overfitting. And the next step, again, flattening. Let me go back to my original graphic, if I have it. Where is it? Yeah, right there. Now, after our convolutional and pooling, you can have any number of this. Before it goes into these dense layers, okay, or the deep layers, we do something called flattening. It's basically a fancy term again. It's nothing but until this point, we are dealing with this 2D, right? So from here and on, it is just 1D, like one list. So we are just converting our 2D to 1D. So that's what our flattening is. So I hope that's what I referred to here. So we are unwrapping or whatever the pooled feature map is, we are just converting that into a single column. That's what flattening is. And the reason why we are doing that, because the artificial neural network input requires a long vector. That's pretty much it. Now, the values, the input, the flattened input, right, goes into this deep or dense layer. And think of this as each point here, okay, is like a neuron, okay? And each neuron is associated with something called weight, bias, and activation function. Okay, so these are the three things. For example, if the weight is 0, it's like killing this neuron. There is nothing, there is no neuron here, right? So it's not contributing to anything. And if the weight is very high, that means it has a high contribution compared to others with low weights. So this is kind of like random forest. Remember, I talked about features. Some features are important, some features are not important. So in this case, we are not talking about features. We are actually talking about individual neurons and their weights. And if the weight is high, okay, that's a good neuron. And bias is almost, think of bias as a threshold. If the bias is above certain threshold, then that neuron is active and contributing. If the bias is certain below threshold, then that neuron is dead again. That's not contributing towards my feed forward. Activation function, I'm going to talk about that in a second, so let me park that topic. Okay, so anyway, so the input is going into this deep or dense layers, and the output again is going to the next layer. And for this neuron, again, it's getting input from somewhere, and then the output is going to a bunch of other neurons and so on. So these are all called hidden layers. This is where, again, the deep learning term actually is coming from, right? So if you have a lots of layers, you have this deep learning, not just one single learning based on one single feature like we do in random forest. Okay, so and the final layer is the output layer. Obviously, what it's doing is giving us an output like prediction. Okay, moving on, more terms. Now, we looked at single neuron here, right? So why is it called a neuron? Obviously, these are all neural networks. And why are they called neuron? Well, they're called neuron because it tries to mimic the biological neuron, right? And for those biologists, who are watching this video, you probably know, this structure. For the material scientists and not non-biologists, you have a neuron where you have the cell body and then an axon and you have synapses, right, that are used for communicating with other neural cells or other neurons. Okay, and then these are the dendrites right there. So if you look at the equivalent function here, again, how is this working? It gets signal from somewhere and then it transmits the signal via these axons, and then synapses connect to these other neurons. So similarly, if you look at the neurons that we have here, there are a bunch of dendrites, okay, that are supplying signal to my neuron. Okay, so again, if you look at this single neuron here, the signals are coming from other neurons, or call these as dendrites, for example, and the neuron has to make a decision whether I should transmit this or not transmit it, right? So that's what neurons are doing. Should I transmit this message or not transmit this message? Again, I'm not a biologist, so I cannot tell you how the human neuron or biological neuron actually works in terms of making decisions whether it should transmit or not, but let's focus on artificial neuron for now. Okay, so it goes through this activation function. Okay, so as the name suggests, the activation function, again, I'm going to talk about that in a minute, but there are various forms and shapes that you can use for activation function. But let's say the information or the value uh, here is above the threshold determined by the activation function, then the signal gets transmitted. Then you get some sort of an output. If it's not, then it's a dead neuron. In a way, again, it's activation is just one of the three parameters: weight, bias, and activation. These are the three things that helps then this artificial neuron make a decision. Now, activation function, talking about it, again, I copied this slide right off the internet. You can go ahead and research each and one of these. Sigmoid function is the most, or at least used to be the most common activation function. Again, I believe I talked about this when we talked about multilinear regressions and a couple of other topics in the past. But when it comes to convolutional neural networks, the ReLU is the most commonly used activation function. Okay, and this is how it looks like when you plot it. Okay, and why is it good? Why is it great? Again, that's a topic by itself. Okay, so go ahead and investigate that if you're curious about this topic. The whole point of this tutorial is to provide you a high-level overview of the terminology that gets used as part of our coding. So now, one of the other parameters that we have to define is the optimizer. In fact, this is the most important. This is what makes it, this is almost like the center of our convolutional neural networks. So Adam is the name of the optimizer that we are going to use in convolutional neural networks. Again, there are various choices for the optimizers. And of course, the choice of which optimizer that you actually pick, the choice of the optimizer makes the difference, is the difference between whether you get good results in a few minutes or hours or days. Okay, uh, and Adam is very similar to the stochastic gradient descent. This is again, if you have, let's say, a well and you're trying to find the minimum inside this well, okay, then stochastic gradient descent. In fact, I believe I have a slide kind of alludes to that, talks about this gradient descent, but it's a great, I mean, the invention of this gradient descent made machine learning or deep learning possible on the computers. Otherwise, that tremendous amount of computations that it takes to find this minimum in our loss function is pretty incredible. The type of calculations that we need to do. So Adam is the most often used for convolutional neural networks, and here is again a graph that I got out of the internet that actually plots a few of the options that are available. And as you can see, the cost function, the training cost with Adam is very minimal. So obviously that compared to the others, that seems to be the best choice. Okay, so we always use the optimizer Adam. And I just mentioned loss function. Again, I did mention about loss function when we talked about linear regression, right? A loss function is a method of evaluating how well your algorithm models your data set. Okay. Uh, Now, if you have a very good prediction, let's say you have a very good model or prediction, you'll have a very low loss function. So, which means when you start your training, initially the loss function or the loss value would be very high. And as you iterate through the process, the loss value gets lower and lower. So, and finally, at some point, you got to stop and assuming that, okay, you have a loss function where your return on investment is not any better, as you keep going through multiple iteration. Now, the one that we use for convolutional neural network is called cross entropy loss function. It's a commonly used one for CNNs, and I believe it is based on these probabilities that go between 0 and 1. And again, I did read this up a long time ago, and if you don't if you don't think about this every day, you know how easy it is to forget things, right? So please go ahead and read about cross entropy. And for convolutional neural networks, by default, I always use just cross entropy. uh, Now, like I mentioned earlier, mean squared error is an example of basic loss function. When we were doing linear regression, I talked about how if you have a whole bunch of data points that are scattered, we are trying to figure out how well the line actually fits. We look at the distances between the predicted and actual, and then square it, and then difference. So that is the least mean square difference. And every time we fit a line, it's actually minimizing this mean squared error. So this is the loss function for linear regression. In fact, I believe I have a graphic here. So you can see initially we start up here, uh, when we start up here, you can actually see, I'll wait for the graphic. You see how the step size is very high, very large, and now the step size actually gets slower and slower as the fit gets better. And look at the cost at step 1, it's 10, step 2, 2, and so on. It actually, the cost is minimizing, and at some point the cost doesn't go any smaller. So that means we probably found the minima, okay? And the step sizes between, you see how the step size between the first and the second is so large. This is not as much, and then the next ones are not as much, and so on. This is called learning rate. How fast are we actually learning? And the learning rate obviously changes, yeah, as you can see here. So that's another term, learning rate. Let me introduce a few other terms and then we should be done, I promise. Epoch and other terms. So when data is too big, okay, when you have like thousands and thousands of images, we cannot just load everything into the computer at the same time, which means we need to break it into smaller batches so the system can handle it. So one epoch is when an entire data set is passed forward and backward through the neural networks. Okay, so there is a feed forward. So when the data is going through, I hate to do this, but when the data is going through from this step to the next step to the next step to the next step to the next step, this is called feed forward. Okay, it's going in the forward direction. At this step, it's actually going to look at, okay, what is the value that I got, like what is the prediction and what is the actual, and then it goes back and then it changes the weights and activation functions, and that is the backward. Okay, so one full forward, one backward is one epoch for the entire data. Where are we? Right here. Okay, so one epoch is when entire data set, okay, all chunks that we break it here is passed through the forward and backward. Okay, once. Now, a batch size is the number of training samples. So if we have a lot of data, we can divide that into 2 batches, 3 batches, 4 batches, right? So that is the batch size. And number of iterations is just number of passes, number of times it went through. So a quick example is, let's say we have 100 training samples. Okay, so batch size, let's say we set it to 25. We say, okay, my computer cannot handle more than 25 samples at a time or 25 images at a time. So which means it takes 4 iterations to complete one epoch. I hope that makes sense. Okay, after one epoch, my neural network would have actually went through each and every one of these 100 training samples, both forward and backward. Okay, so now how many epochs should we do? Like how many times does the system see, these? So if you actually do only one epoch, for example, you don't have good fit. because you start with very bad fit, right? And then iteratively it improves every time you go through these, and new weights are assigned to the neurons. So initially you get underfitting. At some point you have appropriate number of epochs. That's a great fit, right? So at some point you're going to get the best results. But if you keep doing this, then you may run into an issue of overfitting, where you're actually fitting this very well to the data. It looks amazing, right? But this is not generalized enough. If you actually send new data that the system never saw before, then it's not going to work very well. This is obviously what we refer to as overfitting. So what is the best one? What is the right number of epochs? I have no idea. No one knows. It completely depends on the problem, on your problem. So if all your cancer cells, that you're trying to segment, or malarial cells that you're trying to segment, look pretty much the same way, then it may take only a few epochs. But you have very diverse looking cells that, images of the cells, then it may take a lot more epochs. So this is about experimentation. This is where a lot of people are still trying to do research in deep learning to understand exactly how things are working. So these are the fundamentals. But for now, we have to just look at the empirical evidence by working on your data, looking at the results, saying that, okay, this is not enough, going back. Okay, so that's a lot of discussion. Now it's time for us to start coding. So in the next tutorial, let's go ahead and jump into the coding. But again, quick summary. Let's now go ahead and look back at the code. So I hope now it makes sense for us, for you, I mean, for us, about what keras actually means. Right? This is where, based on the TensorFlow library, where we are actually pulling all of our toolkit. So convolutional 2D layer is, again, it's the convolutional layer, and then we do the max pooling after that, and then we normalize the results to make sure, okay, there is no very high, very small values. And then we drop out just to make sure. This is our way of regularizing, or this is our way of actually making sure we are not doing overfitting. And after that, I'm doing another set of convolution, max pooling, batch, and dropout. So this is the second time. And then I say, okay, after these two, I want to feed that into my dense layers. So I'm going to flatten it, into a single vector, and then feed it to the dense layer. I called it hidden one here. And then in the dense layer, which activation are we going to use? Remember, I mentioned ReLU is the one that we are going to use most of the time. And once that's done, I'm going to normalize again, and I'm going to do the dropout again, and then do another dense layer, normalize, and dropout. This is how I chose to design my neural network. You can design it any way you want, right? But this is how I picked. And also you can pick pre-designed neural networks like VGG and a whole bunch of others. Again, let's not get into that discussion right now. Okay, and finally my output layer is the dense layer, where my activation is sigmoid. Okay, so I use sigmoid in this case. You can use, again, different types of activations like I mentioned earlier. And finally, when we actually model it, then as part of our modeling, we're going to use Adam as the optimizer, and categorical cross entropy. I mean, I talked about cross entropy as part of our as our loss function. So I hope this code actually makes sense. And in the next tutorial, we're going to just get our data ready, copy these lines of code, and then literally print out the results and see how accurate our deep learning is. So I hope you find this tutorial to be educational and informative. If so, please go ahead and like this tutorial and subscribe to my channel. Thank you very much for your attention.